Alright, ladies and gentlemen, welcome back for another round. This is Mr. Doolin, and I thank you so much for tuning in. Today what we're going to do, ladies and gents, is we're going to take a look at converting our measured values. So imagine this scenario. I have a balance that measures in grams. And the problem is that I have to report to my boss all of my masses that I record in pounds. So do I have to go buy a new balance? Well, actually balances can be pretty expensive based on the precision. So the good news is that I really don't have to. I can actually just convert grams to pounds. So today we're going to show you how to do these conversions so that we can measure with the equipment we have and then report those values in any unit we want. And once again, one of the primary goals today during these conversions is actually to maintain the proper number of significant figures, and that's absolutely necessary to maintain that level of confidence and precision that we actually had when we made the original measurement. Now, before we get started, one thing that we do need to know how to deal with is really big numbers and really small numbers. So the first example I'll give you is actually Planck's constant, and I'm going to go ahead and write this number out because it's really tiny, right? So I'm going to go 0 point and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and then 31, 32, 33, and then 6, 6, 3. And this is Planck's constant. So really tiny. It's actually used to determine the amount of energy in a single photon of light, which is why it is so tiny, right? And if we look at it, we can actually see and estimate, I guess not estimate, but we know and understand that there's only 3 significant figures in that number, right? All of these zeros here at the beginning, these leading zeros, are just placeholders, right? To push that all the way over there in that deep zero hole. The next example I'll share with you is Avogadro's number. Well, Avogadro's number, remember we talked about a couple of lectures ago that the standard unit of measurement for amounts in chemistry is the mole. Well, Avogadro's number actually describes that amount. Remember I said the mole was similar to a dozen. We know a dozen means 12, so what number of things does a mole actually constitute? And so here we go, we'll do 602. Avogadro's number is a really large number, by the way. And then we'll start putting zeros here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then 21, right? And that's Avogadro's number, right? A really large number. And once again, what we do is we look at and we see these 602 right here. There's 3 significant figures in this number, and the rest of them are just placeholders. So how do we deal with these? Because I don't know about you, but I do not want to write all these zeros out if I'm doing a calculation with one of these numbers. Well, the good news is we've got scientific notation. And scientific notation really exists so that we can write these really large numbers or these really tiny numbers in a nice, easy, I guess, lazy man's fashion, if you will. So scientific notation, we've got a number, right? And this is going to be any number times 10 to some power. And that's the general setup of what scientific notation looks like. Now this number right here, a couple of things about it. It should be between 1 and 10, right? So normally the easy way to think about that is the decimal always goes after the first number. And that'll keep it between 1 and 10, right? And then also this is where we take care of our significant figures, right? So both of these numbers that we're looking at, Planck's constant and Avogadro's number, we notice both of them have 3 significant figures. So guess what this number would be? For each one of those numbers, it would only be 3 significant figures. So this is where that number is where we maintain the proper number of significant figures. This 10 right here, this accounts for those placeholder zeros. And then the exponent, which I have denoted as in here, accounts for the number of times we move the decimal. Now something we want to know and remember about the exponent is that if it's a negative exponent, the decimal actually moves left, and if it's a positive exponent, the decimal actually moves right. And so now let's check and see if we can go back up to our numbers and Planck's constant and Avogadro's number and write those with scientific notation so that we actually don't have to write out all those zeros. So with Planck's constant, I'm going to go 6.63, again, because that's my number, and then it's going to be times 10, and then I got to figure out, right? Notice I put my decimal right there. How many times would I have to move it to the left to actually get it back to its original position, which is right here. And that would actually be, I'm going to say negative 34. And notice I'm putting a negative on here because I have to move the decimal from where I put it to where it originally existed. I have to move it to the left to get it there. The other easy way to think about it is if your number is less than 1, then your decimal is going to move to the left. So now let's take a look at Avogadro's number. Well, Avogadro's number again is 3 significant figures, so we're going to do 6.02, right? So again, I'm putting that decimal right there arbitrarily just to keep my number between 1 and 10. And then I'm going to do times 10. And then how many times would I have to move that decimal? Because remember, with the whole number, if there's no decimal shown, it's always understood to be at the end. So there's the decimal in that number, right? I know it doesn't exist, and this is what's tricky, right? Because if I were to put a decimal there, that would actually make all of those zeros significant. So please understand, the decimal is understood to be in that position. It doesn't exist. It doesn't arbitrarily make those zeros significant, but I understand that that's where it would exist if there was a decimal present at all, right? And so really remember that, because don't get yourself confused about when those trailing zeros are significant or not with what I've got on the screen here. And so I know if I'm doing this, I'm actually going to have to move that decimal 23 times to get it back to where it originally would have been found, right? And so now I understand these are easy to write. Those don't take up much space. It just takes a second or two to write them, and that's the purpose of scientific notation. And so now we know how to take care of those really, really big numbers that we're going to run across, and also those really, really, really small numbers that we're going to run across. So now what we're going to do, ladies and gents, is we're going to take a look at the metric system and the metric conversion system. All right, so the first thing that we want to understand is the space unit. Notice I've got it labeled here in a different color. These are our things like grams and meters and liters, right? And I guess mole, our standard units that we went across in that first lecture, those are base units, right? And notice I don't have just a single letter there. If you just have a single letter or in a single abbreviation, then you have a base unit. And then we've got our prefixes. These are metric prefixes here in red. So we've got kilo, hecta, deca, deci, centi, milli, micro, nano, pico, and femto. So like you would have a kilogram or a millimeter, right? And these are all terms that we've been familiar with, and now we understand they're part of the metric prefix system. And what's cool about the metric prefix system is it actually uses prefixes instead of scientific notation. So let's go ahead and make the connections. Kilo would actually be 10 to the third, hecta is 10 to the 2, 10 to the 1, that would be 1. And then this is 10 to the 0 or 1. Deci's 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, and then we start jumping by 3s. This is 10 to the negative 6. Nano is 10 to the negative 9. Pico is 10 to the negative 12. And femto is 10 to the negative 15. And then we would have Planck's constant, right? Planck's constant was actually 10 to the negative 34, and that's all the way down there, right? So rather than using like 1 times 10 to the third meters, we could call it actually 1 kilometer or kilometer, right? And so notice the 10 to the third matches up there with my scientific notation, and rather than writing out the scientific notation, I can just put the prefix of kilo there. And then we also understand if we're really trying to get down to what that measurement is, we'd understand that that would be 1,000 meters. So both of those numbers represent 1,000 meters, right? And so let's go ahead and look at the next example. We would do, let's say I have 1 milliliter. What would that look like in scientific notation? Well, milli is 10 to the negative third, so I'd say 1 times 10 to the negative third liters is what a milliliter would be. Or we could say it would be 0.0011 liters, right? And so notice again, I'm not actually using scientific notation. These are my metric prefix systems, and then what they would look like in their scientific notation and then in standard notation. So now some people have a question, right? Why do I have the big numbers on the left of the base unit and the small prefixes on the right-hand side of the base unit? And I write it this way so that we can very easily, if we memorize it this way, it tells us which way to move the decimal if we're converting. Right, so my question is when I had that 1 kilometer, how did I know that that was 1,000 meters, right? And that's the question. So if I have 1 kilometer, notice I'm right here and I have to go 1, 2, 3 jumps to get over to the base unit, and I'm jumping to the right-hand side. So what that tells me is that if my decimal was right there, I would jump 1, 2, 3 times to get from kilometers to my base unit of meter. Right, and that's why I write it this way. And the easy rule of thumb, and I guess let me do milliliter too, since we put that example up there. So 1 milliliter, I would see milli would be right here, and I'd have to go 1, 3 places to the left to get back in the base unit. So if I guess I could put my 1 here with my decimal, and I go 1, 2, 3, so I'd have 0.001, and that decimal would no longer be there, and that would be my value, right? And so that's where I got these numbers up here, and I knew how to slide that decimal. So the rule for metric conversions, and the way that I'm going to want you to do it, is really just have this metric prefix conversion system that I have up at the top of the page memorized, and then you just know how many times to slide the decimal based on how many times you're jumping. And if you're jumping to the right to get to your converted unit, then you would move the decimal to the right, and if you're jumping left, then you'd move it to the left. Now, the easy way to remember it, the mnemonic that I teach kids, is King Henry died by drinking chocolate milk. And if you'll see that, I actually got kilo, hecta, deca, base unit, deci, centi, and milli. And these are the 6 that you will absolutely be held accountable to during your chemistry journey here. But micro, nano, and pico do pop up. And I went all the way to femto here because, believe it or not, that's actually the level of technology that we're at right now, is that we can actually measure down to femtograms and femtometers. And femto, I guess, liters if you wanted a volume that small. But it's actually amazing to me that we have equipment that can measure with that level of precision. So the next type of conversion that we're going to take a look at is dimensional analysis. And sometimes you'll hear me say that this is really just multiplying by conversion factors. And so we'll look at a couple of examples here. If I had 257 grams and I wanted to know how many pounds that was. So this goes back to my original dilemma, right? How would I get from grams to pounds? Well, there's a couple of things that I need to know. I could Google like how many pounds are in a gram, and if you Googled that, you would see that there's 452.6 grams is equal to 1 pound. And I want y'all to really take a look at how I wrote that, right? I have 2 values in different units that are equal to each other. And what we're going to know is that these values can actually be turned into conversion factors. And so my conversion factors will look like fractions. So with any equality like this, we can get 2 different conversion factors out of it. We could have 452.6 grams is over 1 pound, or we could have it the other way and have 1 pound is equal to 450, and that should be a 2 right there, 452.6. So 452.6 grams is what that is, right? And so either way it works. And so really, how do I know which one of those I'm going to use to convert this? Well, a big rule of thumb with dimensional analysis, and let me go ahead and change color ink here, right, is that diagonal units cancel. And we know that for math, if we have them and we're multiplying fractions, because when you saw me write these conversion factors over here, you see that they are fractions. And we understand that when we're multiplying and dividing fractions, that we can look diagonally with those fractions and things simplify and cancel out. And so units, when they're diagonal to each other, they actually cancel out. And so what I'm going to do here is run through this practice problem with you and say, all right, we're going to start out with 257 grams. I'm going to multiply it by a conversion factor. So I know I'm going to set up a fraction there, and I know I want to cancel out grams. So I'll put that diagonal to each other. Notice these grams are now diagonal because this is really 257 over 1 if you want to see it that way, right? And so what I know is that if I'm trying to get rid of grams, it needs to be diagonal, and then I know I can go straight to pounds here because I have a conversion factor that looks like this. So this is the conversion factor that I would use over here. I'd have 1 pound and 452.6 grams, right? And so what that would equal, I'd go ahead and multiply it out, and I would end up with 257 pounds over 452.6. Notice grams is gone. Grams canceled here, right? So it's not there, and then I would divide this out, and that would equal 0.568 pounds, right? And notice the conversion factor. I started with 3 significant figures here. There were 3 sig figs here, and then I ended with 3 sig figs. So the conversion factor, really important. Write this really big on your paper. The conversion factors will not change the number of significant figures. So let's take a look at another example right here. If I have 3.6 days and I want to know how many seconds that is, right? I don't know that, but let's go ahead and write down a couple of things that we do know that are equal to each other. Well, I know that 60 seconds is equal to 1 minute. I know that 60 minutes is equal to 1 hour, and I know that 24 hours are equal to 1 day. So these are what I know, and what's going to happen is that these are going to get turned into conversion factors. And so remember, it doesn't really, either one can go on top or bottom, and I'm not going to write all of those out because I don't really want to write out 6 different conversion factors. I just want to write the ones I need. So let's go ahead and start going through this, right? So I start with 3.6 days, right? And remember the question was, how do I know what goes on bottom of this first conversion factor? Well, I know I want to cancel out days. And so I go up here and I look, where's days at? Well, days right here. And the only thing that I have that's equal to days is hours. So I know hours has to go on top there, and it would be 24 hours over 1 day. Well, that cancels out days, but now I'm left with hours. I don't want hours, I want seconds. So I'll set up another conversion factor and we'll keep going. I know hours goes on the bottom because that's what I want to cancel. And then I look up here, well, where are hours at? Well, hours are right here, but that's equal to day, and I already used that. Right? And so now hours are here, and I know that hours is equal to minutes, so I'm going to put minutes on top, and I know that there's 60 minutes in 1 hour. And hours cancels out, but I'm still left with minutes, and I don't want minutes, I want seconds, so I come back over here, and I'm going to write minutes down, and then I guess minutes is here and here, but we already used that one, right? So we're going to use this with seconds. And so it'd be 60 seconds per 1 minute. I'd go ahead and cancel that out, and I know no matter what spits out here, this is going to be in seconds, right? And to do this, it's just multiplying fractions. Remember, with multiplying fractions, we multiply everything across the top, we multiply everything across the bottom, and then we divide, right? So 3.6 times 24 times 60 times 60, that's actually going to equal 311,040. But remember, we have to maintain significant figures. There was only 2 significant figures here, so we only want 2 significant figures here. So to get 2 sig figs out of that, what we have to understand is that I'm going to have to go ahead and say, I know the 3 and the 1 are there, so I'm going to do 3, 1, and then I just need zeros, right? Zeros for placeholders. So I need 1, 2, 3, 4 zeros for placeholders. So that's going to be 310,000 seconds. Right? And that keeps my 2 sig figs that I needed, and it has everything in the proper place value. Right? So now the other way to write this, because if you don't want to get used to writing those zeros, I can actually, notice I have a decimal there, but the decimal actually goes at the end. So, but that's where I would put it if I was writing it in scientific notation. So it'd be 3.1, and then I'm going to do times. So if I did have a decimal there, I'd go 1, 2, 3, 4, 5. So times 10 to the 5th seconds, and both of those are equivalent numbers, right? If I slid this decimal all over to the right, I would have 310,000. So both of the same numbers, and however you want to write those, I'm comfortable with having you do either one. I would suggest, though, that you probably know how to do both, because you never know how I'm going to present those answer choices to you on tests and quizzes. And so the last thing that we're going to look at today, ladies and gents, is a special type of dimensional analysis. And you'll hear me refer to this as stoichiometry. So say it with me, stoichiometry. And stoichiometry exists in chemistry. And really what we're going to do is we're going to use stoichiometry to convert between this unit of a mole, right? Remember, that's the quantity we use. That's an amount in chemistry. And what we know about a mole is that 1 mole is equal to, we already saw Avogadro's number, so 6.02 times 10 to the 23rd, and those would be particles, right? And particles can mean a lot of different things, but we'll get into that later. Just right now, just know, think in your head like a particle of dirt. Like if you had a mole of them, you'd have 6.02 times 10 to the 23rd particles of dirt, right? If you had a mole of calculators, you would have 6.02 times 10 to the 23rd calculators. So particles are really just the substance, the thing that we're dealing with there. The other thing that we know is that 1 mole is equal to 22.4 liters of gas at STP. And again, we'll understand what STP is later on, but right now just understand that at a standard temperature and pressure, a mole of gas will occupy 22.4 liters of volume. So if you had an expandable balloon at STP and you put a mole of gas in it, it would expand to 22.4 liters because that's what the volume would be. So we've got mole is also equal to something called formula mass, as long as that formula mass is in grams. All right, and formula mass is really just how much does a molecule or a substance weigh. And I'm not going to teach you how to calculate that yet. I'm actually just going to give you those formula masses as you would need them. And then later on in this class, we'll teach you how to calculate formula mass. But we can do stoichiometry from day one because stoichiometry is really just dimensional analysis. And remember, these things that we have written over here on the right, these can be turned into conversion factors. And if we can turn something into a conversion factor, we can use dimensional analysis and that idea that diagonal units cancel to actually calculate and convert values. So I'm going to go through a couple of examples with you. Notice I've written over here calcium chloride formula mass is 110.98 grams per mole, right? Calcium chloride is also abbreviated, just so you know, as CaCl2, because I'm going to use the abbreviation rather than writing out calcium chloride because I'm lazy like that. So, but we know that a formula mass, or I guess the molecule, if I had a mole of them, weighs 110.98 grams is what that is, right? But just understand, right, that's what the formula mass is for calcium chloride. So that would insert right here, right? So 1 mole of calcium chloride would be equal to 110.98 grams, right? And that's what this conversion factor tells me. And so let's go and do this. My example, if I have 81 grams of calcium chloride, right? And I want to know how many particles, right? How many actual individual CaCl2s do I have in that 81 grams of calcium chloride? And so let's get to it, right? Dimensional analysis. We're going to write our original value, which is 81 grams of calcium chloride, and then we're going to set up a conversion factor, right? So I'm going to put grams down here because that's what I'm trying to cancel. And then let's see if we can go directly to particles. Right? Let's see if we can do it this way and just go in one step. So I go up here and I look, right? Grams is right here, but grams is only equal and equivalent to a mole, right? I can't actually use particles anywhere here, right? So formula mass is equal to a mole, and then particles is equal to a mole. So this I can't actually do because I don't have a conversion factor that relates those two values. So what we will say here is that we'll go and do this another way, and we'll say that 81 grams of calcium chloride, and then we'll set this conversion factor up here, and then we'll use what we can go to, and we'll say mole. And so what this is going to be is this is where that 110.98 would go, right? Because I know that for every 1 mole, I should have 110.98 because that's the formula mass, right? For calcium chloride, and that's what goes there with that conversion factor. Then I would set up the next one, because again, that cancels out grams, and I didn't want moles, I wanted particles. So now I'm going to have to cancel out mole, and I come up here and I look, all right, moles is equal to particles in this manner, right? So I'll put particles here, I'll use Avogadro's number, 6.02 times 10 to the 23rd, and that would be 1 mole. And then now I've canceled out mole, and I'm left with particles, so I know exactly what I need. And if you type that into the calculator, you will actually end up with 4.4 times 10 to the 23rd, right? And that's your value. And then sometimes you'll see me write this in an engineering notation, and I'll put 4.4 E23. And those numbers are the same thing. That E stands for the times 10. And this is a shorthand notation that you'll see in textbooks and things like that. And plus, that's the way the calculator spits it out. And if you've ever wondered what that E over on the right-hand side of a really big number on your calculator means, it means times 10, and then whatever number's over there is the exponent. All right, so the next example I'm going to do with you, notice I erased everything there. I've kept the conversion factors over here on the right-hand side, so you would just keep going down your page. But I've given you a different formula mass over here. So now we have the formula mass for vinegar. And so again, that would go right here with formula mass, which means 60.052 grams of vinegar is equal to 1 mole of vinegar. All right, so my problem that we're going to do together, I have 3.68 moles of vinegar. And I want to know, if I had that many moles of vinegar, how many grams of vinegar would I actually have? And so let's go ahead and set this up. So I'll do 3.68 moles, and we'll keep vinegar in here. I'm just going to write that in long notation. And then I'm going to set up my conversion factor. Well, I know I'm going to try and cancel out mole, and then I'm going to look up here in my conversion factors, and I'm going to look and see, do I have something that relates, because I want grams, do I have something that relates grams and moles? And you know we do, right? So it's this bottom one with formula mass. So I'm going to go up here and I'm going to put grams. So notice this is the unit in grams, right? So grams goes up there, and then so it'll be 1 mole, and then this number in front of grams would be the formula mass, which is this value up here. So 60.052 0.52 grams, right? And I know some of you are getting nervous, like, okay, well, what if you don't give me formula mass? How do I calculate that? And I promise I'll give you all the formula masses that you need until I teach you how to do it, and then I'll rely on you being able to calculate those formula masses on your own, right? But for right now, I'll give you the formula masses. I'm just testing you to see and trying to teach you how to use these conversion factors to do the dimensional analysis, all right? So we set that up. We see that moles cancels out, and that would come out and be grams of vinegar, and that's actually what we wanted, right? So all I do is multiply across the top, and I would actually end up with 221 grams of vinegar. And I want to go ahead and point this out too. Notice your calculator spit out something different than this, but what did I do, right? I did this on the last one and I didn't say anything about it, right? The last one was 2 sig figs to start with, and we had to have 2 sig figs at the end. This one over here is 3 sig figs, and then we have to have 3 sig figs at the end, and that's why I'm rounding that way. All right, so always be sure that after you do something, our conversion factors are not going to change the significant figures. We're always going to check our original number for significant figures, and that has to match up with what we end up with over here, and that's why we would report this as 221 grams of vinegar. So there we go, ladies and gents, all different types of conversions today that you're going to run across in chemistry for the whole year. As a matter of fact, we're going to learn, and we're learning all those conversions today. I know that's a lot. If you have any questions, I'll see you in class.